The fourth one is derivative of the quotient of functions. If we have quotient of functions, means f over g, derivative of that is always what you have to do is derivative of the numerator times the denominator. Mind you that the denominator has no derivative. Now minus this moment derivative of the denominator multiplied by the numerator. This moment the numerator is not derivative, divided by the denominator, the whole squared. That is always the pattern of how we deal with the derivative of quotient of functions. Quotient means like a rational function. Whenever one function, rational function is actually limited to ratio of two polynomials, but in this case quotient means it could be any function over any other function. You have to note that because most of the time students make a mistake when they make derivative. F over g, the whole derivative, is not equal to derivative of the numerator divided by the derivative of the denominator. It rather goes in this way rather than that way. So generally derivative of quotients is not equal to the quotient of derivatives. It means it's not like that, but rather like this. Example, find the derivative of f of x is equal to tangent of x. It doesn't require us to directly plug in tangent of x into the formula for derivative, formula for slope, but rather f of x, which is tangent of x, can be written as a quotient of sine to cosine. That is sine x divided by cosine x. So the way we write is derivative of sine x multiplied by cosine x minus derivative of cosine x multiplied by sine x divided by cosine x the whole squared. And it is important for you to note that tan x derivative is not the same as sine x derivative over cosine x derivative. This is the wrong way to do, but rather the way you have to do is derivative of sine, that is the numerator, multiplied by the denominator without derivative, minus derivative of the denominator times the numerator without derivative divided by the denominator the whole squared. So this is, I have written it again here so that you will be able to see. Sine x derivative, that is cosine x, and this cosine x is already there, minus cosine x derivative is minus sine x, that sine x is already existing. So what is cos x times cos x is cos square x, minus of minus sine x times sine x is sine square x. And as you know, from Pythagoras identity, cos square x plus sine square x is 1. So this is equal to 1. So 1 over cos square x, that is called sec square x. So the derivative of tan x is sec square x, and that is the way we have to apply the quotient rule of derivative in order to find the problem of tangent of x. Derivative of power function. Let f of x is equal to x to the power of n, where n is a positive integer. Actually, we have derived this one in another tutorial also. And it turns out that derivative of x to the power of n is always n. The power becomes the coefficient times x times the power of n minus 1. You reduce 1 from the power and you bring the power to become the coefficient. And if k of x is 1 over x to the power of n, you can rewrite this one as x to the power of minus n, and you can make the derivative as minus n times, you can make the derivative as minus n times x to the power of minus n minus 1. So you can rewrite this one as minus n over x to the power of n plus 1, which is this one. Or you can, if you want to apply the quotient rule, we can use the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the numerator squared, and then after simplification you will also get the same result. For example, if f of x is 1 over x to the power of 4, its derivative is, according to this formula, simply minus 4 divided by x to the power of 4 plus 1, that is 5. The sixth one is derivative of composition of functions. By composition of function, we mean, for example, let k of x be this fog, means this f of g of x. That is f of g of x. That's called a composition of function. Then this f of g of x, it is derivative, or this one, first of all, can be written as f of g of x. That is the way it is abbreviated here. So you first derivate the external function. You have to first derivate the external function, f derivative, as a function of the argument of the inner functions, that is g of x, multiplied by now the derivative of g as a function of its inner argument. And it goes on like this. That is a pattern. For example, if f of x is sine of t to the power of 10, this can be considered as a composition of function, because on the one hand we see a power function that is something power of 10. On the other hand, we can also see a trigonometric function that is sine of t. So in order to rewrite this one as a composition of function, we can do so by letting u to be sine of t, so that f of u could be u to the power of 10. Now it looks like a kind of polynomial, but this argument is a trigonometric function. So that's the kind of composition of a polynomial function as an argument of a trigonometric function. That is what is meant by a trigonometric function being an argument of a polynomial function. That is a composition of function. So the way we do is we make a derivative of f derivative of u is 10 times u to the power of 9. U derivative is cosine of t. And then by plugging in and expressing our answer in terms of the original variables, the derivative of x is 10 times, because u is already sine t to the power of 9, times derivative of the inner function itself, that is u derivative, which is cosine of t. That is the way we make derivative of this kind of composition of functions. This last part here is something that is coming from that part. This kind of derivative rule is known as the chain rule also. If y is a function of x and x is a function of t, then we can write y of x of t. And its derivative is y of x of t is y derivative of x of t times x derivative of t. So, for example, if we have y is equal to tangent of cosine of x cubed, this is an argument. An argument of cosine is this polynomial function. An argument of tangent function is cosine function, which has in turn an argument of this polynomial function. So where we make derivative of this kind of function, first we start with the outer function, derivative of tangent, as an argument of everything inside it, multiplied by derivative of the cosine function as an argument of what is inside it. In this particular case is a polynomial. Finally multiplied by derivative of this very inner function, that is the polynomial function. So here is the way we go. If we have a function f of g of h of k of x, that k of x is an argument of h of k of x is an argument of g of h of k of x is an argument of f. That is the way one function is composed within another function. So the derivative of this kind of function is like f derivative of that is the very outer function as an argument of everything inside, multiplied by g derivative of what is inside g, multiplied by derivative of h multiplied by what is inside h, multiplied by derivative of k as an argument of what is inside, and so on. That is the way these kind of derivatives take the form. With this kind of problem, we always begin with the derivative of the outer function as an argument of everything inside it, then the derivative of the middle function as an argument of what is inside this middle function, and finally the derivative of the inner function as an argument of its inner variable. And that is the way composition of function is derivated. Let us now be back to the problem that we have started with, that is y is equal to tangent of cosine of x cubed. Derivative of tangent is sec square as an argument of everything inside, that is cos of x cubed, multiplied by derivative of cosine is minus sine as an argument of what is inside it, that is x cubed, multiplied by derivative of these polynomial functions, that is 3x squared. Everything else is just talking about that. And you always, it's very simple, and you always derive the very outermost function as an argument of what is inside, and keep going until you finish everything. Now we are on the stage of making derivative of logarithms. For example, if you are interested to find the derivative of y is equal to ln x, because ln x is nothing but it is simply ln x means is logarithm of x to the base e. That is what is meant by ln x. Ln x is simply the logarithm of x to the base e, where e is the irrational number 2.71828 and so on. So if y is equal to ln x, then if I'm interested to find the derivative of y is equal to ln x, the way I should do is to derive logarithmic functions, because logarithm and exponential functions are inverse to each other. I have to first exponentiate my logarithm. To exponentiate a logarithm means to convert my logarithmic expression into an exponential counterpart. So if I make e to the power of, I want to make e to the power of y is equal to e to the power of ln x. E to the power of y is e to the power of y. E to the power of ln x is e to the power of ln x. But e to the power of ln x means is x, because if I have a to the power of b to be c, a is the base root of c, and the b is logarithm of c to the base a. So if I rewrite this one now, a is to the power of b, but b is now logarithm of c to the base a, must be c. So if I have a here, I must have c there. That is the way it happens. And e to the power of ln x means is e to the power of ln x means e to the power of log of x to the base e. I have e there, so I must have x there. That is the way e to the power of ln x becomes x. So e to the power of y derivative must be equal to, I'm making derivative of both sides. That is it. So this e to the power of y, its derivative is always the same, times its argument. This y can also be derivative. It's equal to derivative of x with respect to x is 1. So because I'm requested to find a y derivative, which is this one, now what I should do is, this y derivative must be 1 over e to the power of y. But my e to the power of y is e to the power of ln x, which is 1 over x. So the derivative of ln x is what? 1 over x. Derivative of exponentials. To derive exponentials, we have to convert them into logarithms. In order to make derivative of logarithms, it is advisable to exponentiate them. If you are given a logarithm, exponentiate it. If you are given exponential function, convert them into logarithms. So in this case, for example, I'm given y is equal to a to the power of x, which is what? An exponential function. So I have to convert that into logarithm. This is y is equal to a to the power of x. I will take the natural logarithm of both sides. Then ln y is equal to ln of a to the power of x, which is x ln a. And then I will make a derivative of this side and derivative of that side. Derivative of ln of y is equal to derivative of this one, which is ln a times x derivative, which is simply ln a. Derivative of ln of y is y derivative over y. So y derivative is simply y ln a, but my y means is a to the power of x, so it is a to the power of x ln a. That is the way we make derivative of exponential functions. Here are some exercises.